All right, I'm talking about the competitive aspects of the competition. So this is what Greg asked me to talk about: how we compete, how we attack the problems, and briefly going over the object detection search software. A general overview that we'll talk about a little bit more. So mostly competition. So you probably heard this story, right? The two middle-aged hunters who emerge from their hut to be faced with a hungry lion. One yells the first, and the second one says, "Can't outrun a lion." The guy says, "Don't have to run faster than a lion, have to run faster than you." So the point of that is, a lot of people come, you saw that wonderful robot with every possible attachment and probably can break dance, but couldn't pick up a sample. So a lot of people over-engineer. And the thing is, we don't have to have a perfect robot that gets every sample. We have to get one sample more than the other guys. And it's really important to analyze the competition, and there are two phases, right? Most people didn't even get through phase one. And phase one and phase two are really pretty different in what you have to do. And if you spent all your time trying to figure out how to do phase two, but you can't do phase one, you're not going to get there. You need to succeed at one, so that's where you should put most of your chips. But you also have to plan, after you get past one, to do phase two, and the strategy might be totally different. So you really have to do a lot of thinking and a lot of brainstorming. Keep it simple, stupid, right? Over-design is a killer. So you have to go on the hardware side as simple as possible. And I have personal experience with this, having been in a couple of competitions and won national championships. So you simplify on the components and you maximize your expertise. So we happen to have experts in computer vision, and that's our main secret ingredient. The other thing is the overall makeup on the team and the dedication to the team, and sort of maximizing that, having the people who specialize in what they specialize in specialize. So how we're going to win is we're going to outthink and outplay the competition. So here are the challenges. Lots of different objects to pick up, different shapes, different sizes. In some cases we won't know what they look like or what they're made out of until we get there. So we have to be pretty versatile. And so you'd think something like a hand, like the elephant trunk hand that can adapt to everything, that might be the best way to go, but it probably isn't, because you have to be, it's very complex, and you need to be positioned very precisely. Your vision algorithm has to be perfect, your odometry has to match. It's all very complicated to get a hand over an object and pick something up. Instead, if you use a scoop, all that becomes a lot more simpler. But sample detection is a tough issue, and that's where we're spending a lot of our time. And little details are important. So in the case of a scoop, right, if the object happens to be in a little bit hole, the scoop won't get it. You're going over grass, so a scoop that works fine on the carpet where you test it isn't going to work well in grass. So all those little things need to be tested. So it's important to prototype a lot of different things and figure out what works best. So I have two pictures here, right? This is the robot of my 2000 National Championship first team. It was done by a continuation high school. They had over here. So this is my 2000 national championship, continuation high school. Some of the kids were in street gangs. Very simple robot. 4 motors. 1, 2, 3, 4. That beat every other high school in the nation. And it was very good at the phase 1 of the competition. It was a pure scoring machine. It would go out and do the first part of the challenge excellently. It wasn't very good at the second part of the challenge, but it was a type of competition where you had teammates and you could switch them in and out. So they understood the game better than anyone else and had a unique style of play that allowed them to win. They did things differently, not the same as everyone else. They reversed it. They also, had the best use of materials. They didn't have a machine shop. They couldn't weld material. So they used these aluminum extrusions. And at the time, that was brand new, and no one else was using them. And so they had that mechanical advantage. So they had an advantage of expertise and an advantage of understanding the concept. The other thing to do is look and see what's there. So this is how they strip mine down under. Right? So that's a machine that has this huge overhead shovel, and underneath it has a conveyor belt. And I go, wow, that's a pretty good idea for a scoop design for what we want to do. I don't think we'd make it quite that big, but
Scare the competition.
yeah. But the thing is, we got, you got to put the sample in the robot, right? And what's the best way to do that? So that's my gig.
Okay. You would have to take half the surrounding grounds with it, or you would have to take
Well, so what? You don't have extra points for. You don't get deducted if you take some of the stuff back. It's only the sample that counts. It's
Are you
cancelled.
touching the objects one at a time, or do you get all of them and come back, or?
Don't know yet,
Okay.
but you would think, for the first phase, we're just getting the one cached object. So,
What's
let's.
the time limit?
It's
30 minutes.
30 minutes for phase 1 and 2 hours for phase 2, and it's a big area. So that's your power. On the first one, you want to move as fast as possible and get back as fast as possible. And the other one, you want to make sure you can gather enough samples and still have enough power and time to get back. So there's a lot of compute cycles in there.
So while Greg's firing that up, I just would like to add a few more details. There's some questions around what the challenge actually entails, and I think there's some really important details as to why this has been so hard. And first of all, again, the prize money, NASA's giving $1.5 million if you can maximize the points, and then they have a graded series of prizes. The next set down is $500,000 or $750,000, then $500,000, $250,000, $100,000, depending upon how many of these second level samples you get. And the samples are scored by their difficulty. The 30-minute time limit is for the first level, as was mentioned, 2-hour time limit on the second level. There's a very, very strict condition that when you put the samples on board the robot into level 2, when you're collecting multiple samples, they must be separated. They cannot touch, or you get no points for that sample, even though it may have been miraculous that you got 2. If they touch inside the robot, you get no points. And the absolute killer, which actually nailed one team that made it all the way out to the pre-cache sample, as they call it the pre-cache sample because they're assuming some other robot or human actually found this and just made it really easy for you to see. That's why they call it pre-cache. One team actually got it in the time limit, got back to the base, and was 1 centimeter outside,
3 inches.
let's call it an inch, outside of this rectangular painted border on the home platform. And they got nothing, no credit. So that's the kind of precision that's required, and that's the kind of difficulty that warrants that kind of prize money, and also explains why so many, in some cases, very excellent teams with extremely expensive hardware and a lot of brain power have yet to to actually master the challenge.
Is this the first year they've done this?
This is now, will be
This
the
will be the
fourth year.
Every year it's the same prize one?
Yes, because they haven't had to give any away.
And they keep on lowering the bar.
Yes,
Right.
the first year the grass was way too long.
The grass is way too long, you had 15 minutes, right?
Okay, I got
It had to boot up all by itself,
As a
or
kid,
they had
yeah.
the NASA people had to boot it for you.
Yeah, yeah.
Now, you get to start and it's in like a pause
I
mode.
get it now, so we're going on and-
You're gonna sleep.
There we go. Okay, so the way this competition works is you don't even get any money if you do better than somebody else. The scoring is absolute. If people tie, then there's a sharing of the money and so on. And so the maximum amount of money that any team has won is $5,000, and that's for getting out within 30 minutes and collecting this sample that starts about 200 feet away. How do we know it's about 200 feet away? Because we looked at that satellite image and used Google Maps as a measuring tool to figure out it's about 200 feet away. And so the very first thing we absolutely have to be able to do is see this thing using computer vision, autonomous computer vision, from 200 feet away on a grass field under unknown conditions. Cloudy skies, sunny skies, brown grass, green grass, trees behind it, trees not behind it. We don't know.
So don't you know where it is ahead of time?
Okay,
Why,
so-
why can't you just drive to the general area and then look for it?
Right, so there are, in level 1, they position the robot facing the sample to give everybody a fighting chance of at least just driving straight. And in fact, you can hear on some of the videos, some of the teams cheering on their robot saying, just go straight, just go straight. The problem is going straight on a rough shot, a grass field is virtually impossible unless you really know what you're doing. But yes, you have a slightly better chance in level 2 by just sort of winging it for the first few meters or 10 or 20 meters and then hoping it comes into view. Fortunately, from the test I'll show you that we've done already in the field, we have a pretty good chance of seeing it, detecting it. In level 2, which is where you're hopefully going to actually get, again, you have to retrieve the pre-cache sample. The sample itself is in the same location. However, they put your robot on the back of a truck to simulate the roughness of landing on the planet. I am not kidding. And they truck it in to the starting area. And now it can be positioned in any one of 3 starting positions, and they will angle the robot within a 120-degree sector. So 60 degrees to the left or 60 degrees to the right. So now you really do have to use vision to detect that pre-cache sample. So if you have any thought of coming back with even partial reimbursement of all the money you spent on the project, you're going to want to be able to see it from 200 feet away. So the computer vision question is, where's Waldo? And here's a pretty classic computer vision problem. We have the target on the top isolated, and then we have a bunch of lookalikes on the bottom. And the question is, how can you get a computer vision algorithm to automatically pull out the one or more matching samples on the bottom? In this case, there's exactly one matching sample, whereas there are a lot of distractors. And it's kind of fun to see in your own brain, what do you think you just did to try to pull that out? And there are sort of 3 general categories, I would say, of how you would go about this problem. The first is template matching, which I'll describe in a moment, and it turns out that's really, really good at our particular challenge, surprisingly. The next one is feature matching, where you're looking for example, the stripes on those shirts, where they tend to be a little bit more sophisticated, like surf and sift features that you've probably heard of, which look at the gradient patterns around different points in the image. And the third is machine learning, where you say, let's just give the computer vision system many, many visual samples of the object we're trying to detect, and many, many other samples of scenes or objects that we don't want to detect. And during the training phase, we'll tell it which ones we want to detect and which ones we don't want to detect. And using any of a large variety of learning algorithms, you can usually get a machine vision system to select out the one you want to detect. Turns out I think that's going to be a very, very difficult, if not impossible thing to do in this particular challenge. So, what have we done so far? Well, OpenCV, as you know, is the Open Computer Vision Library, has every tool you could possibly imagine for doing any of these particular strategies: template matching, feature matching, machine learning, and anything else you want to come up with. And or I should say, in this particular case, I was sort of in charge of doing the initial field testing of what might work and what might not work on realistic images taken from a camera in the field. And it turns out template matching works very well. And OpenCV, this is an actual result of OpenCV running on this exact slide, pulling out the matching sample in the rows below in 30 milliseconds. So that's a pretty quick return in terms of detecting that sample. However, this is a very, very clean, simple situation where we have sharp edges, everything's in focus, and it's basically a graphic. Next slide, please. Oh, there we go. So, how does the real world look? I don't think this is.
Well,
We just lost level 1. Oh, there's. Can we put it in like a slideshow show mode up here? There we go. Okay, so how does the real world look? So first of all, quickly, who can see the pre-cached sample in that image?
Especially now that.
Wow.
Square highlighted.
Boy, that was just like 3 hands out of the entire. So you can see how tough it is. Ah! It bends.
Slide showing now.
Oh no, I don't want a slideshow.
there's a pause button.
I want presentation mode is what I wanted. Sorry. Oh, this is in this silly Mac preview thing. It just go full screen. I thought you had a real computer here running Ubuntu. Just hit spacebar? Okay. So, if you didn't see it, it's down here. And this is a picture taken, as I'll show you in a few moments. It was necessary, first of all, to use a zoom lens, as you can imagine, from 200 feet away. This is a 200 millimeter zoom lens. So from 200 feet away, even at 200 millimeter zoom, you can see how small that sample is. And I chose this particular picture deliberately for tonight because you can see how washed out the grass is, even with a completely auto adjusting camera, doing everything possible to keep things in focus, keep color balance, keep light balance, and so on. You're still going to get this kind of over or underexposed image. The best solution I was able to find for detecting the sample after 2 months of playing with it. 6 weeks of various algorithms. I tried machine learning with histogram gradients. I tried histogram matching color spaces, all the different color spaces, plus a few new ones that got invented along the way. Some machine learning and feature matching. The problem with these tiny little samples, especially given how homogeneous the bulk of the object is, there are very few traditional features. So when it comes to sift and surf, you might get 3 points on this thing out of the millions and millions that are in that image from all the other distracting objects. And when you take another picture, you'll get 3 totally different points on the same object. So feature matching is really tough to do. Like template matching, where you simply take a little picture of the object and slide it across the target image in this case, or the test image in this case at different scales, works out really well. What the white boxes, I don't know if you can see the white boxes. The white boxes are potential matches. And so what I do basically is set a fairly low threshold on the match and then see if a number of them overlap in a similar region. And that helps pull out the best match, and almost within 95% to 100% accuracy now we can actually detect the sample under different conditions. This is what the template matching is actually doing. I'm not sure if you can see this. This is the correlation map. So as you drag that little picture across the little picture of the sample across the test image, it just computes the cross correlation at each overlap point, and the correlation value is plotted as the whiteness of the image. So you can see the maximum whiteness is this little dot here, and that's in fact where the object was detected.
How
So-
does it deal with rotation?
Rotation in what sense? This sense?
Does it do these convolutions by rotating that sample,
No.
or just has to be fixed orientation?
Fixed orientation, but one thing I didn't say is I put in 2 templates, and one was for anything down.
So you went for a couple.
But yes, so I went for a couple. You
We
can
have
put
lots
it,
of templates of the top.
yeah, you can actually put in as many templates as you want,
Time.
and it just adds to the time cost. This time cost right now on a 4 megapixel image, scanning at 5 different scales, is just under a second on an i5, which is fine. We've got lots of time to really make sure where the image is before we move forward. And then we can continue to take pictures, of course, and analyze them as the robot's moving toward what it thought was the first location. And it can update its best guess.
Have you tried it if it is slightly tilted, like it's on sloping ground, or one end of it's got a pebble underneath it?
So it turns out we're actually doing a very fuzzy match. And that's actually one of the reasons template matching succeeds. Behind the scenes in the actual program that we're running here, the very first thing we do is we blur the image, believe it or not. And that's actually a very standard technique in this kind of object detection, because you want to get rid of the noise. And noise is in these little tiny details that don't make any difference, or in fact distract you. So the very first thing was we blur with a Gaussian filter. And believe it or not, we then run a 2 times pyramid down filter, which actually cuts both the width and the height in half twice. So I even reduce the detail further before I actually run the template across the test image. And so what we're actually matching is a white blob. So forget about the exact shape of this thing. We're not matching any detail on this whatsoever, just a white blob. And this can be very troubling in some environments. For example, I'm not sure if you can see it in these test images.
A bit too soft.
Can you scroll up to that one? Thank you. Okay, so I'll just scroll. Okay. This one. Here are 4 successful hits that we're all taking to the same part, but were relatively difficult. And you can see in the upper left one, there are all sorts of white boxes in the trees behind. Fortunately, in the actual competition, as far as we can tell from the satellite image and from a street view that I think Gertz found, which was awesome, on Google Maps, we're not going to have real distractors right behind the sample from the point of view of the robot sitting on the platform. So I'm hopefully testing this in a much more difficult environment than we'll actually face for that level 1 situation. But you can see the white boxes in the upper left picture around all these little white blobs. And remember I said we're really just detecting white blobs, but they're pretty weak because I have the threshold fairly low. They're just coming up as a threshold low. And enough of them overlapped over the actual sample where you see the red box, so we were able to outvote the lower correlation values. Similarly on the right, the lower left. Now the lower left answers your question about rotation. This one's actually matching the template that I used that just has the object lying on its side.
So Patrick,
Yes,
you've got that big white trash can in that lower left one too, and that's
right, but that is way beyond the scales at which I'm matching. So one of the things we do know is from the distances that we know we're going to encounter and the actual physical size of the object, which we also know we can put an upper and lower bound on how big the object can be. That's very important. That's a really good question.
And one thing to also notice is that these are on the vertical side. They're up in the vertical plane, right? And we only have to deal with things on the ground. So as you drive, right, these things stay on the ground and these things go up in the air.
Yeah.
So you realize, okay, that's something that's a false. So we don't have to deal with testing them again.
Yeah, so one of the things that I haven't even begun to test is now, let's do this multiple times. First of all, we need a mobile platform, and Gertz and I have just sort of finished up our own little miniature mobile platform, so we can now put this out, the camera on a mobile platform, have it detect it, have it do its first detection, drive in the direction that it thinks, take another picture, and now update probabilistically where it thinks the sample is based on multiple images as it moves. And as Greg has said, any matches in the top part of the frame should start moving off the frame through the top, and so they'll just disappear and won't necessarily get loaded back in. The last thing I want to say is that one of the common problems in computer vision object detection is you get a solution that works really, really well for one scenario, but then fails utterly in another. This is particularly true of machine learning algorithms, where the machine learning algorithm overlearns the particular training set that you use, the particular samples that you use, so it fits them very well. But the moment you bring in some variation from a different environment, different lighting conditions, different backgrounds, different distracting objects, all of a sudden it fails miserably because it didn't generalize what sort of the overall features were that you were looking for. So the next test was to go to using exactly the same parameters and changing nothing in the software. I took another batch of sample of images. There we go. In a completely different park. This is in the Stanford Oval on the upper left, and this is behind where I work on the lower right, where the grass isn't even green. And you can see, again, we get a very good template match. So with the exact same parameters under a completely different environment. So I think that's it.
One of the things is all these images are available too, plus the code. So you can come up and run your own OpenCV test, make your own templates and try. You can take your samples, reduce them down to size, then actually, run OpenCV and see if it works for you. Next was going to be Ralph, but he's sick. So he's got a cool kind of navigation presentation that we'll have to wait for another day. So it's now how to pick things up. So we have Alan and whoever wants to participate in the pickup aspect of it.
I'm around. This stuff is show and tell like your stuff right now. Quick question about the camera.
Yeah.
What kind of camera are you using?
We're going to use a higher-end digital SLR. So I've got a Canon D7.
So you're not going to go stereo?
Well, stereo will be used in navigation. So pretty much you've got kind of like, we need to find potential targets to go investigate, right? So we have an OpenCV that says, we think this is something that isn't natural, it's a sample, right? So you think of this as a garbage collection task, right? If it's not grass, if it's not dirt, if it's not something that's vertical, go pick it up, right? So you can almost exclude everything and just pick up things that show up that's not grass. So we've trained it to pick up a sample. So you go and look, I think there's a sample over there, you drive closer to it, you get closer, oh, it's a sample.
Okay, so it's basically a high-end global shutter camera.
Right, and then as you get closer, now it's going to come into the field of view of the navigation cameras for the robot that will then take over and drive it directly to that object. So you're just trying to kind of video servo them to the location so the other cameras can start picking it up, and they're good in like the 10-meter range. So, right. So this has actually been quite entertaining to see other ideas on how to pick things up.
Yeah, this was, I actually...
Mike?
Oh.
No, it's Alan.
How come you're so loud and okay. All right. So my inspiration was that mining machine I showed you before, and my other inspiration is I'm a Da Vinci fan. Everyone knows that I like to make little Da Vinci machines. And what Da Vinci would always do is he would have one source of energy, one motor, or in this case, one waterfall, and that he would use to power multiple machines to sort of automate it. So I didn't bring the automate, I have them in the car. But what I thought is, we want to keep it simple, so one motor, and the first prototype is just the rake, literally the rake. I believe in reusing materials as I find them. And as I was walking one day, I saw one of my neighbors had thrown out a busted plastic rake, and I thought that would be okay. And we actually demoed this at our meeting, and I made it just to get the tennis balls. So someone said, hey, see if you can get this with it too. And we went and I tried to get the big object, and it just shattered the rake totally. So now the rake is sloppy, so it's just a wire thing. So the idea is to see what you can pick up, test it on a platform, and then modify it. So I wasn't aware that the samples couldn't touch. So
Don't worry about that.
Okay. Oh, I'm gonna be. So what the next step is to add a couple of gears, a couple of belts, and put a conveyor belt going on the other side. So once it picks the sample up, there's a belt that can pull it back into the belly of the beast. And hopefully, the idea is, because this is an unprecise mechanism, we don't know exactly what all the samples are going to be like or what they're made of. We want to make it as flexible as possible so we can get as whatever material we can. And I'm voting for this as opposed to a hand that can be very precise, but I may get outvoted.
Yeah, so I'm looking at that, and that reminds me of some things I've seen in the past, but it's a little different. And I'd just like to point out, we have about 100 years experience building machines to go pick up various different kinds of objects of various shapes and sizes, of various kinds of terrain, of various kinds of grasses. And they're made by companies with names like New Holland and International Harvester and John Deere.
Yeah.
And I'm thinking, it'd be worth taking a trip over to the Central Valley and visiting an implement dealer and look at the grain heads on combines
Sure.
and the front ends of hay balers and things like that. Because I'm an old farm boy, and I know that a front end of a hay baler can pick up a rock if you're not careful.
Yeah.
And but there's more to the reel than what you've got there, right? What's that?
And the neighborhood cats.
Yeah. And gophers and whatnot.
No, my first thought as I started thinking about this is to go look at mining machines.
Yeah.
Because the first thing I looked at is like the tunnel excavators. Because I remember seeing a machine like this. I don't recall if it was for strip mining or something like that. It was like on Modern Marvels or something like that. And I said, well, that kind of mining machine where it does this and that at the same time.
Yeah. Well, I mean, if you look at the front end of a grain head, right? It's trying to pick things up out of a grassy field and rough terrain. You're going to have a rake mechanism, something like that, made out of spring teeth, but it's going to be rotating this way, and that's going to be at the bottom.
Yeah.
And there will be another reel on top, and then that will go into a conveyor. And I think you're missing the bottom counter rotating part.
Yeah, no, that's what I was thinking about adding to it on the bottom part. So I wanted to see how well this would work, and it turns out it picks up the tennis ball and that pretty easily. So with a little bit of it doesn't pick up the hockey puck because that's a little too small. The other thing, this is going over grass, so one of the things that might happen is if it's in a little declivity, that it's not going to get it.
Well, yeah, and that's why you need the lower counter rotating reel.
Yeah. Okay.
What's your new robot's name?
Well, it's maxed out.
This is
It's team maxed out. I don't know if we have a separate name for the robot, but I assume
It's max. It's max.
It's max. Okay.
Yeah.
Right.
Max.
That
Max,
is a
Max Mini and Max 1 and Max 2. And who knows? All right.
that's
so Steve-
executive decision
Yeah. So,
out of my control.
so Steve's also been working on picking things up, and we've got a couple people on the picking up because this is mechanically it's a challenge, but software-wise, it's got some interesting apart. So he's made one in his kitchen.